On the first day of July, 2025, astronomers made a discovery that would shake the scientific world to its core. They identified 3I Atlas, an interstellar comet racing through space at nearly 124,000 miles per hour heading toward Mars. As it swept past the red planet, NASA's continuous stream of telemetry abruptly went silent, leaving experts without data during the most critical window. The sudden blackout of the world's most advanced observation systems raised immediate concern. Why had every major eye in the sky gone blind? And why did early findings suggest that this object might not be natural, but instead something constructed? The mystery surrounding 3I Atlas began with that blackout and deepened with every passing day. The comet officially entered astronomical records under the designation 3I Atlas, marking it as the third confirmed interstellar visitor to traverse our solar system. Its detection came through a synchronized network of ground-based telescopes rather than a single observatory. Automated logs captured a faint but rapid streak of light moving across the night sky clocked at astonishing speeds. Within hours, the Minor Planet Center issued alerts describing its hyperbolic trajectory, indicating it was not gravitationally bound to the Sun. This was not an ordinary comet. The object's inbound path originated from beyond the solar system, slicing through the orbital plane of the planets, rather than approaching from above or below. Early imagery only fueled speculation. NASA's Perseverance rover briefly captured what appeared to be a bright line across the Martian sky. Initially thought to reveal its shape, the feature was later identified as an exposure artifact, leaving the comet's true form unknown. Amateur and professional astronomers alike anticipated clearer results as the object approached Mars. Expectation ran high that the encounter would yield unprecedented close-up images and spectra. Instead, a wave of confusion followed, as NASA's data channels abruptly failed. When 3I Atlas made its closest approach to Mars in early October, 2025 researchers around the world waited for high-definition imaging and spectral readings from NASA's orbiters. But what they received were broken links and silence. The agency's website displayed maintenance notices while its usual image galleries stopped updating. The Perseverance rover's live feeds ceased for the first time in months. All of this coincided exactly with the comet's passage on October 3rd and 4th. A United States government shutdown had just begun, pausing most operations and leaving missions to run on minimal support. Only essential safety data continued to transmit. Requests for special targeting, such as opportunistic imaging of 3I Atlas, never went through. Internal reports later revealed that the Mars Reconnaissance Orbiter had not been reprogrammed to capture deep space imagery during the encounter. While NASA remained silent, the European Space Agency continued to observe. Their Mars Express and Trace Gas Orbiter missions released summaries and raw images within days, maintaining open-access archives. The contrast was striking. Europe's lower-resolution data remained available, while the higher-quality American perspective was missing entirely. The absence of NASA's imagery left a glaring gap in the scientific record, prompting fierce debate over whether this was coincidence or deliberate suppression. Despite global efforts, the images that did reach researchers were ambiguous. Long exposures required to capture the faint light of 3I Atlas caused the fast-moving object to smear across detectors, creating the illusion of an elongated cigar shape. Attempts to enhance these frames yielded only hazy envelopes and diffuse halos. The comet's nucleus remained unresolved. Signal-noise ratios hovered at the threshold of usability, and background interference created artifacts that mimicked real features. The result was a dataset rich in confusion, forcing scientists to rely on spectroscopy and polarimetry to infer its nature. These techniques revealed partial chemical fingerprints, but the blurred imagery made it impossible to confirm the object's form. With the visual record inconclusive, the investigation shifted toward orbital analysis and compositional clues. Among orbital experts, 3I Atlas has become a subject of fascination for its extraordinary precision. Unlike Oumuamua and Borisov, whose paths cut sharply through the solar system, Atlas travels almost perfectly within the ecliptic plane, deviating less than 5 degrees from the flat disk where planets orbit. For a body arriving from interstellar space, such alignment defies expectation. Models predict random trajectories, yet Atlas glides in a path that threads near Mars, Earth, and Jupiter in succession, forming a sequence of planetary flybys unseen in any previous observation. Statistical analyses estimate the odds of such alignment at less than 1 in a million. Some astrophysicists suggest that natural chance alone cannot explain it. Mass estimates add another layer of mystery. Calculations based on brightness and trajectory imply a mass of roughly 33 billion metric tons, far exceeding previous interstellar objects. Despite active outgassing, its orbit shows almost no deviation, a sign of extreme inertia. This behavior contradicts what is typically observed in comets, which are easily perturbed by their own jets. Such resilience implies a structure denser and more cohesive than loose ice or rock, raising questions about its internal composition. The so-called missing pebbles problem only deepens the puzzle. If nature can produce such a massive interstellar object, smaller fragments should exist. Yet decades of surveys have revealed none, suggesting something highly atypical about Atlas's formation. Spectroscopic data have proven equally perplexing. Observations from the Very Large Telescope in KEK show strong cyanide and carbon monoxide lines consistent with common comet chemistry. But the dust composition tells a different story. Dominant silicate grains point to a rocky warm origin, while the presence of abundant nickel and lack of iron invert normal solar system ratios. Some researchers have proposed the existence of nickel-carbonyl compounds, which form under rare and extreme laboratory conditions. The resilience of the comet was dramatically demonstrated on September 25 when a powerful solar coronal mass ejection struck it. Most comets disintegrate under such stress, but Atlas merely expanded slightly, then stabilized, as though capable of self-regulation. No fragments were detected. Polarimetric studies have revealed yet another anomaly. The scattered sunlight from Atlas shows strong negative polarization, meaning it reflects light in ways opposite to typical icy bodies. Laboratory analogs suggest that only complex or engineered surfaces such as metallic flakes, hollow shells, or spiky aggregates can produce such behavior. The degree of polarization measured exceeds anything seen before, adding to speculation that this object might be more than a natural formation. The orbital choreography of 3I Atlas remains a mathematical enigma. It hugs the ecliptic with uncanny precision, moving from Mars to Earth and onward to Jupiter in a sequence that appears intentional. While statistical caution persists among researchers, the alignment pattern remains unique among all known interstellar travelers. The shape inferred from photometric analyses suggests a long, narrow structure, possibly several kilometers in length, with a high length-to-width ratio. Such a design would minimize drag and radiation stress, ideal for long, interstellar journeys. The combination of elongated form, extraordinary stability, and resistance to solar forces challenges the boundaries of what nature alone could produce. Scientists now debate three competing theories. The first, known as the Trojan probe hypothesis, proposes that Atlas is a mostly natural object, subtly modified for interstellar reconnaissance. The precision of its orbit and durability support this idea, though no direct evidence of technology has yet been detected. The second, advanced by Dr. Suzanne Frame, views Atlas as a planetary seed, a massive fragment expelled from a young solar system capable of seeding new worlds. This theory explains its mass and composition, but remains unproven. The third and most conservative interpretation treats Atlas as an extreme natural comet. However, mounting inconsistencies strain this explanation and require increasingly improbable coincidences to hold true. Each hypothesis offers pieces of the puzzle, but none complete it. Every hour that 3I Atlas remains intact, it carries immense kinetic energy far surpassing any human-made object. Scientists continue to monitor its trajectory for shifts, outgassing, or disintegration. Any fragmentation could unleash forces rivaling planetary-scale impacts. The European Space Agency's JUICE mission is expected to capture new data in November 2025 as it travels through the outer solar system, though the results will not reach Earth until early 2026. For many researchers, this represents the final chance to unravel the mystery of 3I Atlas before it disappears into the dark. Beyond that moment, the answers to its origin, composition, and purpose may remain unknown for generations.